So this example they gave us before, they asked us to find a mean wait time. We actually didn't do that because there's so many on there. I went through and put those two in my calculator already. You don't have to do it. But just to find what the standard deviation is going to be, I'll just run through my program real quick. Let me show you what I did. So I put all of my Wendy's people in L2 and all of my McDonald's people in L3. And I just stored them there. And so now, if I want to find my stats, but I put my stuff in L2, what I'm going to do is I'm going to go to Stat, Calc, 1-bar stats. I don't want to just hit Enter because then it will look in L1 and I didn't put my stuff in L1. So whenever you do 1-bar stats, it always defaults to L1. And we'll talk more about that in 3.3. So, you're going to run 1-bar stats. And then after it, you're just going to type in an L2. So to get this, you're going to hit the second button, and then the 2, and your L2 should show up. So if you put numbers in L1 for a problem, and then for some reason you went away from that problem and you're trying to do something else, but you don't want to delete those things in L1 because you don't want to have to put them back in again, you can use your second list, and that's going to be fine. The only thing is if you put it in L2, when you run your 1-bar stats, you have to specify that it's not the first list. So you just do second 2, do L2, and then it's going to look at your L2 and it's going to give you these values instead. Okay. So that's for my Wendy's people. And this was a random sample of people who go through the lines. This is a sample. I'm going to use my S and not my sigma. So, it's my pen. This one. Samples, we're going to use S. So my standard deviation for Wendy's, so it was point something, 738. And then for McDonald's, I actually put those people in L3. So when I come to run my 1-bar stats for that, I'll go 1-bar stats, but I put them in L3, so I'll do second 3, and I wrote L3 right there. So now I get S of 1.265. All right, so what do these numbers mean? Standard deviation is a measure of spread, so how much variation there is to it, how spread out these things are. So the higher your standard deviation, the more spread out it's going to be. So for this one, since McDonald's has a higher standard deviation, we're going to say that McDonald's data is going to be more spread out on the number line than Wendy's is. So I'd say since standard deviation spread, McDonald's data is more spread out than, bless you, Wendy's. All right, and that makes sense because if we look back at the histograms that are earlier in our notes, we've got McDonald's. This is a little bit more spread out. You've got this peak right here, but then you've got, moderate amounts right here in the middle that spread, and then it goes all the way up to possibly 5 minutes. Here you've got most of your people between half a minute and 2 minutes, and then you've got a few just random people over to the side. But McDonald's is much more spread out than Wendy's is. Wendy's is much more concentrated, kind of clustered around this 1 to 1.5 minute area. You've got people right here, and then just a few people straggling up. So Wendy's is more condensed, McDonald's is more spread out. And that's what your standard deviation is going to tell us. It's just how spread out these things are. So That's what that number represents. So they have these two data sets had the exact same average, but the histograms are going to look a little bit different because McDonald's is more spread out than Wendy's. And then down here it just makes a note that the range, the standard deviation, and technically the variance, none of those are going to be resistant, right? So if you throw in large data values, or if you throw in a really big number, so if somebody goes to Wendy's and they have to end up for some reason waiting 30 minutes, then if you throw that into the histogram, Wendy's is going to be even more spread out because you've got that person over there at 30 minutes. So if you throw in an extreme value for these ones, your range is going to increase and your standard deviation is going to increase quite a bit as well. So the only thing we have so far that's resistant is our median. Technically our mode would be resistant as well, but we don't usually use the mode, so we don't really think about that. We do have one more measure that's resistant, but we won't get that until next week, so just have to wait. All right, so now we're going to move on to what's called the empirical rule. If you took 105, you've seen this briefly in that class, but this is just going to be talking about specifically distributions that are bell-shaped. If you have something that's skewed to the right or to the left, you can't use the empirical rule for it. But as long as it's roughly bell-shaped or approximately bell-shaped, or it's close enough to being bell-shaped, then you can go ahead and use this. So it's going to break it up into, right, so we've got our little bell-shaped curve. So here in the middle we have mu, that's our mean, that's our average. So the average is going to be exactly right here in the middle. If you go up one standard deviation, so if you add one standard deviation, you're going to be about right here. If you go up another one, add another standard deviation, you're going to be right here. If you add another standard deviation, you're going to be right here. If you decrease, so starting right here, if you go down one standard deviation, subtract one standard deviation, you're here. Subtract another one, you're here. Subtract another one, you're here. So that's just what it's representing, is how far away you are in terms of standard deviation. Let's see, I think we talk about z-scores. Okay, so we'll talk about z-scores later. Okay, whoops. Okay, so we're just saying how far away you are from the mean in terms of standard deviation. So if you're one standard deviation above the mean or two standard deviations below the mean, that's what we're going to be looking at here. And we'll come back to it when we talk about z-scores later. But if we look at just the data values that are representing underneath that curve for the entire population, everybody in between these two lines here, so if you go down one standard deviation and up one standard deviation, that represents roughly 68% of your data values. So more than half of your people should be within one standard deviation of the mean. If you go up to two standard deviations, so if you increase to here and here, that's going to be 95% are going to be within two standard deviations. If you go out one further, it's going to be 99.7 are within three standard deviations of the mean. So fill it in. It's already listed there on the graph, but it's going to be 68% of the data lie within one standard deviation of the mean, and then they give you those bounds right there. You've also got 95% are going to be within two standard deviations, and 99.7% are going to be within three standard deviations.